In the last video, we could see what the observer is, what the observer principle is. And in this video, I would like to show you how to design the observer. So just a very short recap what the observer is. So in this case, the x hat is the observer output with which we would like to follow the real state x. So in this case, the goal is x hat should follow the real x as fast as possible and as small error as possible. And the observer algorithm looks like this equation. So the d over dt of x hat is fx hat plus gy plus hu. So the inputs of the observer are the u and the y signals. There is one thing, so this part, which is responsible for the speed and the stability of the observer. And from the last video we could see that f is equal to a minus g multiplied by c transpose, but we don't know the value of g and we have to find the g out. And if we know g, we can obtain f. H is equal to b and g is not known. So f must be stable and fast. This is the starting point of the observer design. So here on the left I am drawing the observer characteristic polynomial. So there is a characteristic polynomial for the observer. Why do we need this? We need it because we have to plan how fast and how stable the observer should be. So we are going to give the observer polynomial on the left. And this is the lambda multiplied by the identity matrix minus f, but f is not known yet. In the next step, we are going to put this equation to here. So f is equal to a minus g multiplied by c transpose, and the eigenvalues are not changed if I take the transpose of the last term. So the transpose of a minus g c transpose. The result of this is the determinant of lambda multiplied by the identity matrix minus a transpose minus c g transpose. And in this equation, in this determinant, the g transpose is the thing we would like to calculate, we would like to design, because we don't know this term. And in the design we are going to give the lambda to the power of n plus p1 lambda to the power of n minus 1 plus p2 lambda to the power of n minus 2 plus etc. pn. And these p's give the behavior of the observer characteristic. If we have a look at to the red side and we go back for a moment to the characteristic polynomial of the closed loop system when we designed not the observer but the controller, we get this closed loop system characteristic polynomial lambda and the identity matrix minus a minus b k transpose, and here the k transpose is not known. This is what we have designed by the Basgura algorithm or by the Ackermann formula. And if you have a closer look at to the green one and to the red one, we can find a similarity. On the right we use A, on the left we use A transpose. On the right we use B, and on the left we use C instead. and on the right we use K transpose to design, and on the left we use G transpose to design. And this similarity is called the duality of the controller observer design. So they are very similar, but there are some differences between them. This is why it's a very easy and a clever way to set up a so-called fictitious system. Fictitious system is coming from the real system, and to prepare not so new equations, we can use the fictitious system. What is the fictitious system? On the left I put some results. So the first is the original system with A, B, C transpose and D. The fictitious system is the second. It means that we have to take the transpose of the system matrix A. We are going to take the transpose of C transpose and put this vector to the place of B of the original system. And we have to take the transpose of B, and it will be the C transpose place of the fictitious system, and D is not changing. And now we have got a fictitious system, which fictitious system has a system matrix not A but A transpose, and a vector not B but C. And for this A transpose and C, we can design a K transpose matrix, K transpose vector by the Basgura technique or by the Ackermann formula. And from this K transpose, we can obtain G. So these are the steps of the design of the observer. Because of duality, we have a very easy way if we know the steps of the controller design. There is another things they have to do on the right. So let us prepare the MC, the controllability matrix, because controllability matrix can be found in the Basgura method and in the Ackermann formula too. So if we prepare a so-called fictitious system, so it means that we use C instead of B and A transpose instead of A. So this is what we can find here. So C, A transpose C, A transpose square C, and so on. And this matrix is the same which I put to here. So C transpose is the first line, C transpose A is the second line, C transpose A square is the third line, and so on. And we have to take the transpose of it to make this equality true. And if we look at, this is the observability matrix transpose. So if we have got a fictitious system, first we do this step. It means we change A to A transpose and we change B to C, but we have to change MC to MO transpose. So after this, we have a very simple way if we use either the Basgura method or the Ackermann formula. So I put here with green the Basgura method and the Ackermann formula with red. So in these equations, we just do the following modifications. So instead of MC, we use MO transpose, and instead of K, we can get G. So the Basgura algorithm, but the Basgura method for G transpose is P transpose minus A transpose, tau inverse, and MO inverse transpose. P transpose is coming from here when we design the observer polynomial. A is the same as in the controller design, so tau is also the same, but we don't use MC, but we use MO. So we have to prepare the observability pages. So in the case of Ackermann formula, we just replace MC to MO transpose and A to A transpose, and everything, every other place is the same, but I have to highlight, we don't use FCL, phi CL. Phi CL is for the closed loop characteristic polynomial when we design the component, but phi O is the observer polynomial here, which is this one, which I highlighted here by black. So this is the observer polynomial. And finally, we can obtain G transpose. Of course, it will be a row vector, and G is an column vector. We can take the transpose. So either we use the vascular method or the Ackermann formula, we can obtain G. And if you know G, we can go back to the very beginning, because we can obtain F as A minus G C transpose, and the observer is ready to use after the design process.